So, okay, welcome to our first office hours. Like I was just saying right before this recording started, two main things we're going to talk about today, an effective EDA, and then SMOKE, dealing with class imbalances. Cool. All right, so first to start, for classification, actually for any machine learning problem, as we know, EDA is fairly important. It gives you a good idea of your data, especially as you're trying to familiarize yourself with the data set. EDA can be very, very important. Now, at a certain point, doing EDA might get harder and harder because you might have more and more features, and it sometimes doesn't make sense to loop through all of your columns and print all of these, I don't know, these histograms or like scatter plots, so on and so forth. So therefore, when it comes to EDA, and if your data set has a lot of columns to the point where you feel like it's not going to be effective to just, do a histogram of every column, before I get into the details of EDA, note that you can actually turn your EDA, or when you can do your EDA, if it makes sense for your project, you can actually do your EDA after you model. Because let's just say you have 100 columns, and through your modeling process, you find that, let's say you do your important features, let's say only like 20 of them are important. So then you just do your post-modeling EDA, which will be very, very similar to what you would have done pre-modeling on those 20 important features. So that's one way to help deal with, high dimensionality data and getting through all of those graphs. Because sometimes as a person, you cannot look at 1,000 graphs. So just know that if you have a lot of columns, and I think most of you don't have, I don't think anyone has more than 30 columns in their data. So you actually should be fine. But if you do have a lot of columns, just know that you can do your EDA after you model. But I do expect to still see some very high level EDA, like exploring your data. You probably are doing some data cleaning at the start as well. I still want to see those processes. Cool. So for an effective EDA, before we get into it, I want to talk about what classification is actually doing, and also the concept of the separability of data. The main purpose of this EDA, and if you want it to feed in very nicely to your classification modeling, or if you want it to be very strongly related to your results of your classification modeling, it helps to think about how your data is distributed across multiple classes. So I'm going to use this example as another one of these built-in data sets on breast cancer. And they basically have a bunch of measurements of, I think, the tumors. And then this data set is basically, is it cancerous or is it not? But for the separability of data, I would say all of the models that we've talked about with regards to classification work better if your data is separable. Now, what does separable mean? Let's just say you have a two-dimensional data set, and I'm just going to draw a janky graph over here. Let's just say this is our feature space, and I have a bunch of tick data points that are over here, and I have a bunch of crosses over here. And let's just say there's only these two features. There's only whatever this X and whatever this Y is. This data is extremely separable, no matter what algorithm you're using. Very, very easy to separate, right? So if we're thinking SVM, the one that we last talked about, hyperplane just goes right there, separated, you're done. Next, if you think about any tree model, anything that's built off of decision trees, you're looking for the best way to segment your space. If you can find this clear line to separate your data, you can very, very accurately classify at least your training data. So this is highly separable data. And this concept of the separability of data does scale up to more and more dimensions. And usually the more dimensions you have, the higher chance you have at finding separability. So then that also brings back the kernel trick that we talked about at the end of last week. So this is separability of data, just in space between your classes. And you can have more classes than this, right? If you have another class, let's say you have this class of, I don't know, hearts over here. As long as they look separable, it will be much easier to classify. And by easier, I mean you're going to get great classification metrics, probably. Most of the time in real life, data does not look like that. So let me clear this up. In real life, data probably looks a little bit more similar to this. So let's just say we have a bunch of ticks over here. And then we have a bunch of X's over here. You probably have data that looks more like this, right? There's gonna be some that are obviously one class over the other, but you're gonna have a bunch that are in the middle. And those are the data points that likely across your different algorithms, some algorithms will be able to separate them, some will not. So that's the idea of separability. And that's gonna come back actually when we talk about dealing with class imbalance a little bit. So hold on to this concept of separability. This is also why baseline model is extremely important. So if your data isn't separable to begin with, you want to have sort of still a starting point. It's very similar to how in the last project we started with like a really crappy model and a low R squared, high RMSE to begin with, just so you can iterate and improve upon that number. There in all of machine learning, there's rarely like a goal of like, okay, no matter what the data set is, I want a 90% accuracy or 90% recall. That is not a thing. So just to be aware. Okay, so let's talk about EDA then. And in this notebook, which is not on the repo yet, but I'll push this after this session just in case I make any changes while I'm going through this. In this repo, I'm going to go over some helpful graphs, and we'll think about these graphs in terms of the separability of data. Cool. So let's talk about continuous variables first. So in this case, our target is categorical, but you also have continuous features. So what would be some helpful graphs for your EDA that can show you how separable your data is? So I would say, I think I made the suggestion before of overlapping histograms or like disk plots. So I do it in two libraries. So this is an example out of Plotly Express, and these are two histograms. So here, this breast cancer data set, we have malignant and benign. And I always forget, I think benign means it's not cancerous and malignant means it is cancerous. If someone knows better, please correct me, but yeah. So based on this graph, and this is just, the two different classes, what does the distribution of this feature of mean radius look like? So out of all the benign tumors, this is a distribution of their mean radius. And out of the malignant tumors, this is the distribution of their mean radius. So you can see that their distributions are quite different. And from this, you can already see, okay, well, if I have a radius of, let's say, about 12 or 13, more than likely, based on our training data, more than likely it's going to be benign. But if you have a radius of, and I should have done it like a little bit transparent to be more clear, but let's say we have like anything above 20, above a radius of 20, and I don't know what these units are, but let's say we have a radius above 20, more than likely it would be malignant just based on the distribution of these histograms. And so something like this, where you can sort of see some ranges of values is more likely to be one over the other, that is a sign of separability. A sign of non-separability is across the two classes, both histograms look exactly the same. That's going to make it very hard for your model to use this feature to do classification. So something to think about. If you're seeing histograms that pretty much like overlap over each other, you might want to take that out of your data set to save on computational power. But I will also say that at this stage, feature selection is not the most important thing for this project, but good to keep in mind. Cool. Next year, I just have an example with Seaborn. Facet grid. I actually, because I don't use Seaborn, I had to do a bit of research over the weekend about this. Facet grid is a pretty neat one because it also does it. It also normalizes it a little bit. So this is the Seaborn example. So this is a disk plot. You can do the Q equal to target. It actually takes in your data frame really nicely like that. But yeah, so these are examples of comparing your continuous features to your categorical classes. So from here, you can sort of see, all right, if it is above like 19, let's just say it's millimeters. If it's above 19, you can pretty safely say that it's going to be a malignant tumor. Versus if it's more in like this range, let's say, definitely if it's like under 9, it's definitely going to be benign based on your training data. Any questions about these graphs? Cool. All right, so what about categorical columns? Now, you conceptually still want to see the same thing, but when it's categorical, as we know, categorical will be zeros and ones, and it's a lot harder to, you can't do a histogram of zeros and ones because it'll just be like a bunch of bars that won't add very much information. So let's just create a categorical column first. We're going to use mean area, and we're going to just create a new column called mean area large that is categorical. So we can see mean area large, value counts. Okay, so fairly even because we split on the median. So we're going to have a bunch of trues and falses. So instead of doing a bunch of histograms, if you're comparing categorical feature to categorical target, I think something like a bar plot is good enough. So this is a Plotly version, and Plotly version, you do a little bit of research on Seaboard because I don't have it normalized like this. But in Plotly, I kind of want to move this away now. Hold on, let me erase this line. Okay, so it's a little bit clearer. Okay, so in Plotly Express, which is this graphing library, you can see that the blue ones are malignant and then the red ones are benign. And this is kind of normalized. Well, I guess not normal, I guess because they're evenly distributed, but these are the ones with large mean area. These are ones with small, large mean area. So what does this show? Fairly separable as well, because if you have a smaller than median area, very, very likely it's going to be benign, versus if it had a large area, you have a much higher chance of it being malignant. So you can sort of see the distribution of your features across your targets. You can do it this way. You can also flip it. So this is an example, I think, with it flipped. Yeah. So Seaborn example, you can see here, malignant, benign, large area is orange, small area is blue. So you can see out of all the benign tumors, most of them are small, and out of all the malignant tumors, mean area is mostly large. So either this graph or this graph, you just want to see the difference in the distribution of the feature with regards to your target. Questions about this? Cool. Now connecting this with your modeling results, let's say you do all of your EDA at the start, and let's say you do either this kind of graph for your categorical variables, this kind of graph for your continuous variables. If you see high separability, very, very likely it's going to come up as an important feature or have a significant coefficient, depending on what model you're using. So what I would love to see is, let's say you finish your modeling up, and let's say you get like 3 most important features, and you want to connect it to your business case. And so let's just say that, okay, for this data set of detecting breast cancer, my business case is I want to start developing early detection methods. And I find one of the most important features is looking at the radius. So maybe develop something that can signal, okay, if the mean radius starts to be above 16, you should start, maybe, I don't know what the threshold would be, but like you can start doing scanning earlier, or like doing some checkups to make sure that you're detecting it early. Just as an example, this is how you turn your non-quantitative feature importances into a quantitative recommendation. So just this as an example, if you see the mean radius being above like 15, it's really up to you how you want to define this radius. Or if you want to be like extra safe, you maybe say like, okay, if it's going above like the range of 10, there's a chance that it might be malignant, and so therefore you want to start doing checkups and stuff like that. Connect it to your business case, but now be quantitative based on your EDA. So that's how you connect your EDA, and that's why EDA can also be important. Cool. Questions before I move on to talk about class imbalances? Okay. All right, so class imbalances. Not every data set that was provided has class imbalance. I think the ones with the most class imbalance are probably the churn data set. So if any of you are working on that one has a pretty high class imbalance. I think it's like almost 90% one class, 10% the other. The car crashes one, depending on what you choose as your target variable, might have some class imbalances. The Terry stops one does have a bunch of class imbalances too, depending on what you choose as your target variable. So yeah, this is just another technique that you can employ to maybe make your models work better. And why it's only maybe, we'll explain mine a little bit. So I'll talk about this in relation to class separability in a little bit, but also when is it appropriate to use rebalancing methods. So let's first take a look at the value counts for this data. So this data has 357 benign, 212 malignant. It's actually not too imbalanced. If I do, I think it's normalized equal true, right? Okay, there we go. So it's about a 60-40 split of your classes. So this is actually not too bad. It's actually fairly evenly spread out, but let's just pretend that this is imbalanced. First, talk about how smote works. So I'm going to use this like really extreme example to demonstrate how smote works. So let's just say I have this data set. We have a bunch of these class zeros, and this is the minority class of class 1. So the orange data points, this is underrepresented in our data set, and we want to use smote to have it equally represented. So smote is a process of creating synthetic data points. And specifically, it doesn't just randomly create synthetic data points. It creates data points within the realm of your existing minority class. What that means is, so let's say we have this data that looks like this at this point. If I employ smote and plot these data points again, notice it looks pretty interesting. It has this very particular shape because your how smote works is going to look at all of the values that exist within the minority class and then only create synthetic data if it falls within that range. So because the data points are here, you're not going to see a one data point like out here, for example. So what does that mean in terms of class separability? If your data is already not separable, doing smote might not help. Because if you have non-separable data, let's just look at these like ticks and crosses again. And let me just erase the ones that are out here. So let's just say the ticks are the minority class. If I employ smote here, and you can see that this is already not very separable. If I employ smote, smote is just going to smote more points within this range. It's not going to increase the separability. Therefore, it might not help our model's performance either. Maybe it will because you're giving more weight to those specific data points, and some models might be able to pick up on that. But again, you're not really increasing the separability of your data. So do take note, don't expect smote to be like a godsend to your imbalance data. It doesn't always work because it does depend on the initial separability of your data. So that's something to keep in mind. Is something, and I do think the separability of data, especially for a classification problem, is an important concept to start to think about. But cool. So that's how smote works. Now, how exactly do you use smote in your project? Oh, before I get to that, questions about, I guess, the process of smote before I dive into how you use it in your project. Cool. This code, by the way, comes from comes from this data source, and that data source actually like walks through a process of smote if you're interested in like doing a more deep dive into that. Oh, if you want to incorporate smote into your pipeline, you can do that too. However, you can't use the scikit-learn pipeline. Smote comes from this library called Imbalance Learn, IMB Learn, that works exactly the same way as scikit-learn, but they also have their own pipeline. You just have to import it from their library, but functionally it does the exact same thing. It still has the .fit, .predict. The instantiation method is just the same. It just comes from a different library. So if you want to incorporate smote into your pipeline, just look out for that. Okay, neat. So moral of the story, creating smote doesn't help the separability of your data at all. There's actually one method that I'm going to talk about towards the end that might. So if you're seeing that your data is not separable, I'm going to show a method later. Okay, so how exactly do you use smote? I think because, I don't know, at least I don't think I remember seeing that in the labs. There's nowhere that shows you exactly how do you implement smote correctly in a way that doesn't lead to data leakage or in a way that doesn't, I don't know, you don't want, because synthetic data is not real data, right? So you don't want to make any predictions of synthetic. So we'll get to this process. So using the same breast cancer data set, I'm just doing my chain test split, same XY. So we only have 455 data points here, X train, Y train. And with our Y train, you can see that it's imbalanced, but not super imbalanced, but it'll work the same way no matter how imbalanced your data is. Okay, so these are the value counts at the start. Next, what we're gonna do is you only fit resample, and fit resample is basically the step of creating these synthetic data points. You only fit it on your X train and Y train. And I highly recommend that you create new variables. for your resample. So here I'm just going to call it X train smote, Y train smote. You actually don't have to transform your test data, and you'll see why in a little bit. So instantiate the smote object, fit resample my train data, and now I went up from 455 to 572 data points. Now I do my value counts. You can see that they've created about 120 benign, oh sorry, not, they've created about 120 malignant data points so that they become exactly 50-50 split. Cool. So now that we've done this smote, notice that I only do this on the trained data. And why I only do this on the trained data is the purpose of smote is just to teach our model slightly different things. Maybe you want to weight that minority class a little bit more by creating some extra data points. But there's no point in making predictions on synthetic data. So let me just fit this classifier first. We're just going to use a random forest. So I'm fitting my random forest, and notice that I'm fitting it on my smoted data. When I'm making any predictions, like for my confusion, for any metrics, you're going to predict on the non-smoted data, because like why make predictions on the however many, especially for this train set, why make predictions on fake data? So just to note, you make your predictions on the regular data. So we're going to do this, and we can just see some confusion matrices. You should still see a little bit of imbalance in your confusion matrix. That's how you know you're doing it the right way. So here you can see this is just the train one. This is the test one. I did not label it, but you will in your projects. But here you can see that on the train, cool, we have perfect prediction. And you can see that these numbers are still imbalanced. Well, they're not 286 on both. So this is still done on the non-smoted data. And then we have this also on the well, you don't transform your test set at all. So you can see here, we just have two misclassifications. So in terms of which part of the process do you do your smote, I would say do your smote as your last step before modeling. So what I mean by that, let's say you want to scale your data, or let's say you want to impute your data. You do all of that before you smote. You just smote your smote will be your penultimate step before modeling, basically. Any questions about this? Okay. In terms of the process of smote, I understand that it's like it's kind of conceptual, a little bit abstract. So any questions? And if like the process is not right in your projects, it's not a big deal. I'll just mention to you when we do our review. Okay, so other rebalancing methods that are not smote, because as you can see, smote doesn't really help with the separability of data. You can also do random over or under sampling. Actually, for the people who are doing the car crashes data set, there are a lot of rows in there. And one method that's absolutely fine to do, because I think there's like maybe 100,000 rows. Your models might take a very long time to run, and I know there are a lot of columns there too. So just know that you can totally just resample an even amount from each class if you would like. I want to talk about this other method called removing Tomek links. Now, Tomek links exists in, I think I have it in the project 3 guidelines somewhere. Let's see. There we go. So I think the documentation here, there's an explanation, but I do want to talk about it as well. So if you want to use the documentation, it comes from the same library as Smote. Oh no, I'll look for it. I need to learn Tomek links. Okay, here we go. Tomek links. I'm going to replace that real quick. Edit link. Okay, there we go. That's all good now. All right, so Tomek links is an undersampling method, whereas for Smote, it was an oversampling because we were creating synthetic data. Tomek links is going to do the opposite. It's going to take your majority class and remove some data points. And Tomek links is actually one of the methods that does increase the separability of your data. And I'll explain that process pretty briefly now. So let's just say that this is our data. You can see that there's a bunch of overlap. There's pretty much like no green ticks that are not in the realm of these red data points. So how does Tomek links work? How it works is it takes a look at your minority data points. So as an example, let's use this green tick that's all the way at the right here. So for any minority data point, what it's going to do is going to look at, okay, this minority data point, I want to try and get my model to recognize that a little bit more. let's find the majority data point that's closest to it and get rid of it. So for that green tick, it's going to see, okay, let's say that this red X is the closest. Oops. Damn. Okay, we'll delete that red X. And it's going to keep doing that process again. Which red X's are next to or closest to the green ticks? We're going to delete those. And so that's why it's called removing Tomek links. I don't know where the word Tomek comes from, to be honest, but it's basically going to remove majority data points that are in the realm of the minority classes. And that, as you can see, I also accidentally erased a bunch of the ticks itself, but as you can see, it does create separation. So if you have very severe class imbalance and you also have a lot of overlapping data and you don't see a lot of separability when you do your EDA, Tomek links might be something to try. Tomek links doesn't immediately level your classes, especially if you have severe imbalance, because you pretty much will only delete the number of X's as you do the number of ticks that you have. But that's also something that you can change in your hyperparameters. Feel free to play around with it. But yeah, pretty neat method because you are preserving all of your minority data points and you're just removing majority data points. Now, yes, it can end up biasing your model a little bit. You might see better results. How do you make sure that that is not being negatively affected by too much? Only do this on your train set and make sure that on your test set, you're seeing improvement. But yeah, that's a pretty neat rebalancing method as well, which you can find the links for on our guidelines. Cool. Now, does anyone have any questions? Those are the two main things I wanted to talk about today. I'm happy to answer any project questions at this point. Also happy to talk about these at one-on-ones this week. Oh, by the way, for those of you who are working in pairs, I know most of you are working by yourselves, but those of you who are working in pairs, if you want to meet as a pair for your one-on-ones, just send each other the Zoom link. You don't have to let me know or anything. Cool. Last call for questions before we call it a day. Going once, going twice. All right. Well, don't forget, presentations will be on Friday, but on Friday, again, same as last time, you don't have to have like your final models or anything. Just want to see where you are and also how you would present your work in progress. So yeah, in terms of presentation format, very, very similar as the last time. So yeah, I don't think I'm going to do an office hour section on that. Sweet. Tomorrow's office hour, I do want to talk about saving your models. If you see on our homeroom, it's called pickling. And pickling is something that was in a phase 1 topic, but it becomes a lot more relevant now once we get into this modeling stuff. So I'm going to talk about that tomorrow. And it's going to actually lead into how you can productionalize your model, which is, we'll talk about tomorrow. Cool. All right. Well, if there are no further questions, feel free to Slack me all if y'all need anything. But if there's nothing else, you all have a good rest of your day and keep working on those projects. Bye, everybody.